Let's practice balancing redox reactions. In our first example here, we're asked to balance this reaction in an acidic solution. Step 1 tells us to split the unbalanced reaction into half reactions. How do we do that? Well, we're going to look for species on both sides of the reaction that have something in common. So for instance, here I see solid iron, and over here there's an iron 2+. So those two things, since they both have iron in them, are going to be part of my first half reaction. If it's on the reactant side, it's going to stay on the reactant side. And the iron 2+ is on the product side, so that's going to stay on the product side in my half reaction. We have manganese in this ion here and manganese 2+ over there. That's going to be our second half reaction. The other thing to note here, how do we figure out the states? Well, ions, anything with a charge, will be aqueous. We do have a solid species in this particular example, and that's okay because it's neutral. But if it's an ion, it's going to be aqueous. So we're done with step 1. Step 2, we're going to identify the reduction half reaction. And as part of that, we also need to identify the oxidation half reaction. We better have one of each. Remember, reduction and oxidation are complementary processes, and you have to have one if you have the other. There needs to be some place for those electrons to go. So in order to accomplish step number 2, I'm going to assign oxidation numbers to everything that I've written here. So solid iron, it's by itself, it's neutral. So it'll have an oxidation number of 0. This is an individual ion. We'll do a +2. Remember the rule that tells us if you have individual ions, then the oxidation number and the charge are one and the same. Over here, I'm going to split the permanganate. I have oxygen. I'll do a -2 on the oxygen. But there's 4 of them. So this side has a -8. The whole thing has to add up to -1. So the manganese must be a +7. Because if I do +7 - 8, I get the -1 that I need. And then this is one of the straightforward ones. Charge and oxidation number are the same. So over here, the iron went from 0 to +2. So it went in the positive direction on the number line. So this is my oxidation half reaction. We're looking at the loss of electrons. Oxidation is loss. Here we have a +7 on the manganese, and then it went down to a +2. So it's going in the negative direction on the number line. Negative to gain. So this is going to be our reduction half reaction. Remember, oil rig, the rig part says reduction is gain. So that's good news. We have an oxidation half reaction and a reduction half reaction. As part of our analysis here, we can also add electrons. So for my oxidation half reaction, we expect the electrons to be a product. And for reduction half reactions, the electrons are going to be on the reactant side. I'll squeeze it in here. Nothing's balanced yet. Typically you need coefficients in front of the electrons, but we'll get there in just a second. In step 3, we're going to balance everything but hydrogen and oxygen. This doesn't really apply here because the iron is already balanced. There's 1 iron on each side. And in this other half reaction, the manganese is already balanced. There's 1 on either side. So we're going to skip to step 4. Step 4 tells us to balance oxygen by adding water. So over here, we're not going to need to do that. Every step doesn't apply to every single half reaction. And since we don't have any oxygen here, we don't need to do step 4 here. However, on this half reaction, we do have 4 oxygens on the left. So that means I'm going to have to add 4 waters to the right. Step 5 then tells us to balance hydrogen by adding H+. And that begs the question, how come we can add H+ and water and not worry about where they're coming from? Well, that's been accounted for. We have aqueous solution, so that's where the water is coming from. And then earlier on, I had already erased it, but I wrote that we're balancing this in an acidic solution. So there's protons, H+ ions, floating around in that solution. And we're just adding them now to our equation where we need them. So step 5 isn't going to apply here because I don't have any hydrogens to worry about. Over here, we have 4 times 2, we have 8 hydrogens on the product side. So I'm going to add 8 hydrogens to the reactant side. And since they're ions, I can label them as aqueous. So step 6, we're going to balance charge now. And this is something new. When we did balancing previously, we never really had to worry about charges. Usually everything's neutral in beginning balancing problems. Here though, we need to worry about charge, and we're going to fix the charge imbalance with electrons. So to do that, I need to write down my charges. Here I have oxygen or iron, solid iron. It's a neutral species, so this is going to have a charge of 0. Yes, it's the oxidation number. There's a lot of overlap between charge and oxidation number, but I really am focusing on charge here. This has a charge of +2. And we can only add electrons. So we can only add negative values to balance the charge. The reaction arrow is a glorified equal sign. So I'm going to change this to a 2. Because 2 times -1 is going to give me a -2. And 0, and then if I add these together, we have another 0. And so then it's balanced by having 2 electrons on the product side. This one's going to be a little bit more complicated. So we have 8 protons. 8 times +1 gives us a charge of +8. The permanganate here, there's just one of them and it carries a -1 charge. We have +2 over here. And the water is a neutral species. So it's going to be a 0. We know that the electrons are on the reactant side because we figured out earlier that this is a reduction reaction. So we're not going to move the electrons. We're just going to figure out how many electrons we need. So +8 and -1, this is +7. So I somehow need to get the 2 sides equal. Well, if we add a -5, 5 times -1 for those 5 electrons, 8 minus 1, 7, plus -5, well then that's going to give me +2 when I add up all the charges. And now both sides are equal to one another. So far so good? So once it's all balanced, now we have 2 balanced half reactions. Now we're going to need to recombine everything. So step 7 tells us to multiply the half reaction so the electrons cancel. The amount that's lost by our oxidation half reaction, the amount of electrons that it loses, has to equal the amount of electrons that are gained by the reduction half reaction. Here we have 2, and here we have 5. So when you're up to this step, you want to think of the least common multiple. 2 and 5 are going to meet at 10. So if I take this whole thing, and I'll put it in parentheses, if I take this whole thing and multiply it by 5, and I distribute the 5 to everybody, that's not going to mess up my balancing, but that is going to give me the 10 electrons I need. Over here, I'm going to do something similar. Except I'm going to multiply this whole thing by 2 and distribute the 2 to every single species. So it's going to affect every single coefficient in that reaction. This step gets kind of messy, and typically at this point I rewrite things. So give me a minute, I'm going to rewrite them, and then we'll proceed to step 8. So I distributed the 5 and the 2 and rewrote both half reactions. One of the things that I like to do is to keep the reaction arrows underneath one another. That's because we can cancel from left to right on the diagonal. So the reactants of one equation will cancel with the products of the other equation, and it works in both directions. So if I see the same exact thing on the reactant side here that I see on the product side here, and they have to match exactly, but I can cancel. So you're canceling on the diagonal. In that direction, things will cancel. You have to cancel your electrons at a minimum. Sometimes there's going to be other species that repeat, like water, and you'll be able to cancel some of the waters. But when you finish this problem, when you present your overall balanced equation, there should be no electrons after step 8. So we're going to be successful here because we have 10 electrons here, and that's going to cancel with the 10 electrons here. There's nothing else that's exactly the same, so that's all I can cancel for this particular example. Just like before, if it's on the reactant side, it stays on the reactant side. So now we're going to add up everything, and you basically just rewrite it. So I have 5 solid iron, the 16 protons, two permanganates, the electrons are gone, they canceled, and so now I'll work on the product side, just adding everything up. I have 5 iron ions, 2 manganese ions, and 8 waters. At this point, it's always nice. It's a lot of work, and you want to make sure you get the problem right. So I always like to do a quick check that it's balanced. So 5 iron, that looks good. I have 16 hydrogens, and there's 16 hydrogens over there. That looks good. 2 manganese, and then 4 times 2, that's 8 oxygens, and we have 8 oxygens over there. So it should be balanced. When you have your overall balanced reaction, it needs to be balanced for elements. It also needs to be balanced for charges. And you can always take a second and check that, and that's a good way to know that you probably got the problem correct. So this is neutral, 0, positive 1, but there's 16. So the charge with the protons will be plus 16. 2 times negative 1, we got a negative 2. So on this side, I'm looking at a plus 14 charge. 5 times plus 2, plus 10 for the charge. 2 times positive 2, I got a plus 4, and 0 from the water. That's a neutral species. So 10 and 4 gives me a plus 14. So we have a charge of positive 14 on the left and positive 14 on the right, and we're good to go. This is done, and we can feel fairly confident in our answer. What we're going to discuss in the next segment is there's additional steps if we need to balance it in a basic solution. But if you're asked to balance something in an acidic solution, your problem is complete after step number 8. We're done. We're going to start this next problem by splitting the unbalanced reaction into half reactions. We're going to look for species that have something in common on both sides. So, for instance here, this ion contains chlorine, and I'm going to keep that with the chloride ion. Then we have a chromium-containing ion, and I'll keep that with the other chromium-containing ion for my second half reaction. Alrighty, after we write out the half reactions, our next step is to figure out where we're going to place the electrons. And we do this by identifying the reactions as either being reduction or oxidation. So for this first one, I'm going to do a -2 on the oxygen. And the whole thing has to add up to -1. So that means my chlorine here has to be a +1. So I got +1 -2 gives me the -1. Over here, the chloride has an oxidation number of -1. So it went in the negative direction on the number line. It gained electrons. Whenever you see a gain of electrons, that's reduction. And we're going to write the electrons then on the reactant side. So let me squeeze that in here. You see a gain of electrons. Over here, hopefully this is our oxidation reaction, because we always want one of the half reactions to be reduction and one of the half reactions to be oxidation. This is a little bit trickier. I would look at the hydroxide ion as a whole. We know hydroxide is a -1. That's its charge, it's not its oxidation number. But at the end of the day, I need to figure out what's going on with chromium. -1 times 4 is a -4. The whole species needs to add up to a -1. So if I do a +3 on chromium, I'm going to have +3 -4 from the 4 hydroxides equals -1. Over here, we'll do a -2 on the oxygen. -2 times 4, -8. Chromium then is going to have to be a +6, so we get to that -2. +6 minus 8 gives me -2. So chromium went from +3 to +6. It went in the positive direction on the number line, positive to lose. Oxidation is loss. So whenever we have an oxidation half reaction, we're going to put the electrons on the product side. So we're done with these first two steps. Now we're on to the third step. Balance everything but hydrogen and oxygen. So always, this step doesn't always apply, but always check. You just want to make sure. If you skip it, it's going to mess up everything. 1 chlorine here, 1 chlorine here. Good to go. 1 chromium here, 1 chromium here, we're good to go. So step 3 doesn't apply. Step 4, balance the oxygen by using water. So I have 1 oxygen here. So I need to put 1 water molecule over here. Let's see what's going on over here and if I can fit it. There's 4 hydroxides, which means I have 4 oxygens on the left side. But we also have 4 oxygens on the right side. So we don't need to do anything. It looks like the oxygen's already balanced for the chromium half reaction. Alrighty then. So step 5 deals with hydrogen. So in step 5, we're going to balance the hydrogen by adding protons, adding H+. Alrighty, over here we have 2 hydrogens. So I'm going to add 2 protons over here to get the hydrogens balanced. Let's see over here, 4 hydrogens, and then there's no hydrogens over here. So let me squeeze in, write a little bit smaller, but I need to squeeze in 4 protons on the product side. And I still have those electrons as well. Sorry. Alrighty. And I'll rewrite this in just a second. I always like to rewrite before I add stuff up. So we are almost there to the rewriting step. Step 6 tells us to balance the charge with the electrons. So in step 6, we're going to consider the coefficients of the electrons. Put up step 7. All right, so charges, different than the oxidation numbers. I'm going to do them in blue. 2 times plus 1, plus 2, charge. This has a -1 charge. Plus 2 and minus 1, what does that give us? That gives us a plus 1 on this side. And then we need to equal a -1. How do we get a +1 to equal -1? Well, if we add 2 electrons, 2 times -1, that's -2. Then those 3 charges will add up to -1, and we're balanced for charge on this side. I ignored the water, but the water is neutral, that's 0. That doesn't carry a charge. Over here, we have a -1, a -2. 4 times plus 1 will give us a +4. So -2 plus 4, we have a +2 on that side, but we need the +2 to equal the -1. We can only add the negative numbers. And so if we put a 3 out in front of our electrons, that's going to give us a -3. So -2 plus 4 minus 3, that's going to give us a -1 on this side. I do this step a little bit fast, and you'll get there. Don't be frustrated. Be like, how's she doing that so fast? Like, take your time. Sometimes at first students will guess. You'll put a number here and always check your charge, and then you're like, oh, that number didn't work out. So then try another number. You can always check your work with this. It just takes a little bit longer, but that's how you learn. So step 7, we need the electrons to cancel. So here we have 2 electrons, and on this one we have 3. The least common multiple between 2 and 3 is 6. So I'm going to take this whole thing, I'll put it in parentheses. I'm going to multiply the one with the chlorine in it by 3. And then over here, the one with the chromium, I'm going to multiply that one by 2. And so again, this is the point I rewrite. This is way too messy for me now. So I'm going to rewrite this, and I'm going to carefully distribute this 3 to every single coefficient in the reaction. On the product side too, we need to get that 3 to every single coefficient. So give me a second to do that. So I've distributed both the 2 and the 3 to the half reactions, and that's what you see written here. This unbalanced equation on top, that was our original problem, and even though I kept it on the board, ignore it. It's not part of what we're doing right now. Right now, we're working on adding up the 2 half reactions. It's critical still on step number 8, when we add up those half reactions to obtain our overall reaction, the electrons must cancel. The final overall reaction should never have electrons in it. So let's see what's canceling. by multiplying, we've successfully gotten rid of the electrons. So cancel the 6 electrons. Remember, again, you can cancel on the diagonal. So we can cancel this way and we can cancel this way. They have to be exactly the same. There's 6 protons over here and 8 protons over there. So that means that we can cancel 6 of them. So I'm going to cross out these 6, and then 6 protons are going to disappear from here, leaving me with 2 protons. And at this point, it doesn't look like we can cancel anything else. We're going to rewrite this, line up your arrows when you're at this step. And that makes it a little bit easier to see, okay, these things are on the reactant side, and when I add up, I'm going to keep everything that I didn't cancel out, and I'm going to keep it on the reactant side. So that's it on the reactant side, just 2 species. And then for the product side, a little bit more going on. We have chloride. So I've added everything up. If the conditions were acidic, we would be done with the problem. However, I erased it again, but it said to balance it in a basic solution, which means instead of having an excess of protons, H+ ions, floating around in that reaction mixture, now we have a bunch of hydroxide ions floating around. Before I proceed to the next step, I still like to check if it's balanced. So let me go through that real quick. I got 3 chlorines on this side, 3 chlorines, 2 chromiums, that looks good. How are we doing on oxygen? So 3 oxygen from here, 8 oxygen, 11 oxygens it looks like on that side. And then 2 times 4, that's 8, plus the other 3, we got 11 oxygens. 8 hydrogens on this side. 2 plus 6, another 8 on that side. We could go through and also check the charges if we want. It should be balanced for elements and charges at this point. And this is balanced in an acidic solution. Let's change it over to basic conditions. We want to eliminate H+, because the H+, the protons, are what's making this acidic. So we do that by essentially neutralizing the H+. If I add 2 hydroxide ions here, I'm going to get water, because you'll recall from previous lectures, we talked about how H+ and OH- gives us water. That's just off to the side to jog our memory here. So if I add 2 hydroxide ions here, I'm going to get rid of the H+. However, we just did all this work. It took us a minute to balance this. I don't want to ruin the balancing. So kind of like with algebra, if I do it to one side, I want to do it to the other side as well. So I'm just going to add 2 hydroxide ions over here. And if we want, we could put them as aqueous because they're ions. So we need to rewrite and potentially see if stuff's going to balance or combine. Over here, when we consider what's going on, there's 2 H+ and 2 OH-. So this basically turns into 2 water molecules. You want to have like a 1-to-1 ratio, and whatever it is, like you add, if it's a 3 and you add 3 hydroxides, then you're going to get 3 waters. And what's interesting here, we're not going to be able to cancel, but there's 2 waters coming out of the addition of the hydroxide. And we already had 3 water molecules that we added earlier to help us balance. So I'm going to add this 2 and this 3 for a total of 5. So let's just rewrite this whole thing, and this will be for the basic conditions. So start with 2 hydroxides, I'm just copying everything else. Just be really neat about this. Like this negative sign here, it's such a pain. It's so easy to miss. And if you miss it, then you're going to get the wrong answer. Just be really neat and systematic. So we have 3 chlorides, and then just keep on copying here. And then at this point, the protons went away, turned into 2 waters, and then I have the 3 other waters, so I'm going to do 5 waters over here. The last thing we could do, and I encourage you all to do this, is check again. It should still be balanced for elements. It should also be balanced for charge. So quick check. Let me look at oxygen, since there seems to be a lot of oxygens in this. So I have 2 oxygens here, another 3 oxygen here, 5 oxygen. This is 8. 5 plus 8. What do we have? 13 oxygens on this side. 8. 2 times 4 is 8 plus another 5. So 13 oxygens on that side. You can go ahead and look at chlorine. There's 3 chlorines on each side. You also want to check charge. If you're going to submit this final answer, this would be the final answer. You want to make sure it's right. So in terms of charge, we have 2 times -1, that's a -2. 3 times -1, that's a -3. 2 times -1, we got a -2. So on this side, it looks like we have, if I can math today, -7. It needs to be equal to the charge on the other side. 3 times -1, -3. 2 times -2, -4, and 0. So that makes me happy. -3 and -4. That's going to give me a -7 over there, and I have a -7 over here. So my final answer, and this is under basic conditions. I know it's basic because we have the hydroxide ion there, and we don't have any H+. My final answer is balanced for both charge and elements. Such a cool problem. It combines multiple things that we've been talking about over the past couple of weeks. So we're given an unbalanced redox reaction, and we see that this is a mass percent problem. And in order to get at our numerator, the amount of oxalate in the sample, we need to do some stoichiometry as well. So lots going on. A little bit of background: oxalic acid, this species right here, is present in plants and vegetables. We're told that in the longer version of the problem. The main plant that I know of that contains oxalic acid would be rhubarb. And rhubarb leaves are really poisonous. The stalks are edible and they're really delicious in like baked goods and stuff, but the leaves are poisonous and you need to discard them. So imagine somebody, they got a whole bunch of rhubarb leaves and they're trying to figure out how much oxalic acid are in those rhubarb leaves. They're titrating the oxalate ion. So once these things are mixed into solution, they start breaking up into their ions. So our information about the oxalic acid will be found by focusing on the oxalate ion. Let's start by balancing the redox reaction. So I'm going to separate this into half reactions. I'll do the permanganate. And the permanganate in our problem up here is the potassium permanganate. They're one and the same, except potassium is a spectator ion, so that's left out. And then that's going to go to manganese in my half reaction. And the other half reaction will be the oxalate. carbon dioxide is the product. Let's see where we're at. Hopefully we have an oxidation, and hopefully one of these is a reduction. So assigning oxidation numbers, I'm going to do a -2 on my oxygen, which gives me a -8 here, meaning manganese must be a +7. +7 minus 8 gives me the -1. This is a +2. So manganese went from +7 to +2. It must have gained electrons in order to do that. When something gains electrons, we're going to write the electrons on the reactant side. Leave a little bit of space there for my coefficient. We know that's coming. Over here with the oxalate, we have -2 on the oxygen. There's 4 of them. -8 on that side. So in order to get to -2 overall, I need a +6 on this side. However, there's 2 carbons and they share that +6 charge or oxidation number. So individually, they're both +3. For carbon dioxide, I'll do a -2 times 2, which is a -4, adds up to 0. So my carbon then must be a +4. So carbon went from +3 to +4, moved in the positive direction on the number line, lost electrons. Therefore, the electrons are going to be products. Whenever you lose electrons, the electrons are on the product side. So we figured out who's reduction, who's oxidation. The next step after that is to balance anything that's not oxygen and not hydrogen. We're all set with manganese. Over here we have 2 carbons on the left side. So I'm going to put a 2 in front of my carbon dioxide, so I have 2 carbons on the right side. So now we're balanced for everything that's not oxygen and hydrogen. Next is to balance oxygen. 4 oxygens over here, so I'll add 4 waters over here. And let's be careful, we got 4 oxygens here. 2 times 2, we got another 4 oxygen. So nothing to balance in terms of oxygen for the oxalate half reaction. Hydrogens. So 8 hydrogens, so I'll put 8 protons on this side. No hydrogens over here, so nothing to do over there. Once everything's balanced, oxygen, hydrogen, everything else, now we deal with electrons. So to do that, we're going to have to look at the charges. I'm going to do that in blue. 8 times +1 is +8. The permanganate here is just a -1. +2 and 0. So I have a +7 on this side and then a +2 on this side. So it looks like I'm going to have to add 5 electrons. So it's going to give me a -5. And then when I do that, I have a +2 on this side and a +2 on that side. Over here, -2. Carbon dioxide is neutral, so this is going to be a 0. And, well, I need a -2. So if I add 2 electrons, that's going to give me the -2 that I need on that side. So now we're balanced for electrons. And then the next step after that, because we're going to add them up again and get an overall equation, we need to multiply so that the electrons cancel. 5 and 2, they're going to meet at 10. So let's take this whole thing and we'll multiply this one by 2. I'll put the 2 over here. And then this one we'll multiply by 5. I'm going to rewrite those so we can add them up. Everything's been rewritten, and I'm at the point now where I want to add up my 2 half reactions. Let's see what's canceling here. So for sure the electrons are canceling. That's super important. And I don't see anything else that's exactly the same along the diagonal. So I'm going to keep everything else. So we wind up with 16 protons, 2 permanganate, 5-oxalate two manganese ions, 10 carbon dioxide, and 8 water. This has to be balanced before I move in and start considering the stoichiometry. So let me do a quick check. I have 16 hydrogens, oxygen's always very telling. 8 oxygen plus another 20, that's 28 oxygens on that side. And then I do have 28 oxygens on the other side. Let me do the charges real quick. That's always a good thing to check. So we have plus 16, 2 times negative 1, we got a negative 2. And then 5 times negative 2, we got a negative 10. So what is that? A plus 4 on this side when we add up all those. And then 2 times positive 2, we got a plus 4. The carbon dioxide and the water are neutral, so they're zeros. Plus 4 does equal plus 4. Since it's balanced for charges and for elements, we know we're done. How do we know we need to do this in an acidic solution? This one's a little bit tricky. Because we're titrating oxalic acid, I'm going to go with the assumption that the titration is done in an acidic solution since we're dealing with an acid. So we can stop here and we don't have to worry about getting rid of the H pluses. We're done. This is balanced. Now on to the stoichiometry. The wording on this problem is tricky. It almost sounds like they have a 10-gram sample of oxalic acid and we could just use molar mass and convert that over to grams. Unfortunately, that's not the case. So the implication here, the way we need to interpret this, is that they have a 10-gram sample containing oxalic acid. So maybe they have 10 grams of rhubarb leaves and they're trying to figure out, well, what is the mass percent of oxalic acid in the 10 grams of rhubarb leaves? So the 10 grams will be our total mass. We're working to find mass percent. How do we find the mass of the oxalic acid? That's going to be accomplished through reaction stoichiometry. That's the whole reason we needed to balance the redox reaction. I'm going to start with the 24 milliliters of potassium permanganate. We know that it has a molarity of 0.11 molar. So we can set up our next conversion factor using the molarity. So there'll be 0.100 moles of potassium permanganate per every 1,000 milliliters of that solution per 1 liter. Milliliters will cancel milliliters. The next conversion factor comes from the formula for potassium permanganate. I want to get rid of potassium permanganate and turn it into permanganate. So I'm just looking at the formula itself and I can say, well, 1 mole of the potassium permanganate contains 1 mole of permanganate. Okay, so after that, we've gotten rid of moles of potassium permanganate. After that, I can use my coefficients of the balanced equation to set up a mole-to-mole conversion factor to figure out what's going on with the oxalic acid. So from the balanced equation, I'm going to grab the 2 in front of the permanganate. So I'm going to say 2 moles of permanganate will react with 5 moles of oxalate. after that, well, we're not interested in oxalate, right? We're interested in oxalic acid. So after that, I'm going to set up a conversion factor using the formula for oxalic acid. I'm going to say 1 mole of oxalate in 1 mole of the oxalic acid. And sometimes, to be perfectly honest, sometimes when I set this up, I skip the formula conversion factors, because with practice we see how it breaks into ions. And if you recognize that it's a 1-to-1 breakdown, then you can kind of get away with skipping the formula conversion factors. But you definitely need this mole-to-mole conversion factor from your balanced equation. You can't circumvent that one. At the end of the day, we need the mass of the oxalic acid. So we'll grab the molar mass of oxalic acid and use that for our last conversion factor. And moles of oxalate cancel with moles of oxalate, moles of oxalic acid with moles of oxalic acid, leaving us with grams of oxalic acid. So when I solved that earlier, I got 0.054024 grams of the oxalic acid. Almost done now. Now we got to take that value and throw it into our mass percent equation. So that's going to go on top. And since we're dealing with a 10-gram sample, that'll go on the bottom. And it's a mass percent, so we're going to multiply by 100%. When I did that and then I rounded it to 3 sig figs, I got 5.40%. And we want to be specific. This will be percent oxalic acid by mass. And that's our final answer.